But hey, let me show you the math way first. And hey, you may have seen this equation before in GChem, and it goes like this. Formal charge, Fc, this equals the number of valence electrons, VEs, okay, minus parentheses, the number of bonds, plus the number of non-bonding electrons. And I'm going to abbreviate that by putting NBEs, okay, non-bonding electrons. Okay, so hey, what this stands for is formal charge equals the number of valence electrons minus the number of bonds added to the number of non-bonding electrons on the atom you're talking about. Hey, so that sounds really complicated when you say it all out like that, but you'll see how simple it is when we apply it in our example. Okay, so hey, in H3O, or oxygen connected to 3 hydrogens, we've been asked to find the formal charge on each individual atom. Arbitrarily, you guys, let's just do the formal charge of oxygen first. Okay, so hey, if we just follow the formula, we can write Fc parentheses oxygen. So this is how you'd write the formal charge of oxygen. And this is going to equal the number of valence electrons oxygen has. Oxygen has 6 valence electrons, right, if you look at the periodic table. Okay, so 6 minus the number of bonds connected to the oxygen, which is 1 bond, 2 bond, 3 bonds. So a number of bonds is 3, added to the number of non-bonding electrons. And all this means is electrons that aren't in bonds, electrons that are in lone pairs, right? And hey, this oxygen has 1, 2 electrons that are non-bonding electrons. So hey, you'd put 2 right here. So hey, 6 minus 3 plus 2 equals a plus 1. Okay, and that's your answer. The formal charge on oxygen in this compound is plus 1. So to indicate that, you draw a little plus sign. Let me do this in blue. You draw a little plus sign with a circle around it right next to that oxygen. If the formal charge had been a negative 1, you'd have drawn a little negative sign with a circle around it like that. Or if the formal charge had been a 0, you'd draw a little 0 with a circle around it, okay? Or you just write nothing next to the atom. Okay, so hey, let me erase this real quick. All right, so now let's check the formal charges on the hydrogens in this compound, okay? Okay, so coincidentally, since all of the hydrogens, each of these hydrogens in this compound have the same number of bonds and non-bonding electrons, it turns out that all the hydrogens in this compound will have the same formal charge. And if you plug all the information into the formal charge formula, you'll find this to be true. So let's do this real quick. So hey, Fc parentheses H, the formal charge of hydrogen, right, equals the number of valence electrons hydrogen has, which is 1 according to the periodic table, right, minus the number of bonds attached to hydrogen, which is, hey, 1 in each case, right, you guys? That's why I said they're all the same. Okay, so, hey, 1 added to the number of non-bonding electrons, which is 0. None of these hydrogens have non-bonding electrons on them, right? Okay, so, hey, 1 minus 1 plus 0 equals 0, right? The formal charge on each of these hydrogens is 0. So we leave the space next to them on the Lewis structure blank. Okay, or you could have drawn a 0 with a circle around it, right? But hey, the reason I said coincidentally that all these hydrogens are the same is because not all atoms have the same formal charges in a compound just because they are the same atom. For example, you guys, just because the formal charge on one oxygen in a compound is plus 1 doesn't mean that all other oxygens in that compound will have a charge of plus 1. You have to find formal charges for each atom in a compound, okay? Okay, so if you're not sure what I mean, go ahead and try this example out on your own. A C double bonded to an oxygen connected to a hydrogen, connected to an oxygen, connected to a hydrogen, connected to a CH3, okay? Okay, so if you determine the formal charge on each of these oxygens, you should find that the formal charge of one oxygen is 0, whereas the formal charge of the other oxygen is a plus 1. And let me just tell you which is which so you can go ahead and check yourself when you get home, okay? So, hey, this oxygen with 3 bonds to him, 1, 2, 3 bonds to that oxygen, has a charge of plus 1. So I'll indicate that with a plus with the circle next to it, right next to that oxygen. Okay? Hey, this oxygen with 2 bonds to it is going to have a charge of 0. Okay? 2 bonds to it is going to have a charge of 0, so I'm not going to draw anything next to him. Okay, so make sure to go home and try this on your own. Do it the math way, and you'll see that not all atoms in a compound, even though they're the same atom, not all of them will have the same charge. This one has a plus charge on it. This one has a 0 charge on it, a neutral charge, right? Hey, so that was the math way, you guys. And it's always good to start out with the math way because it gives you a very structured formula for you to follow. And you get the right answer every time. The problem is, though, when you're eventually asked to draw out entire reactions with compounds on a test, including their formal charges, there's just no way you'll have enough time to figure out the formal charge of each atom by hand in every step of the reaction. You'll need to be able to do it this next way I'm going to show you. And believe me, you guys, this way is so much easier than having to memorize a formula and plug numbers into an equation. All you have to do is use some common sense, okay? All right, so let's erase this real quick. Okay, so there's 2 ways to find formal charge on atoms. We just saw the first way, which was the math way. The math way, right? Now let me show you the second way, the conceptual way. Okay? Okay, so let me first preface this method by telling you that all atoms start out with a certain number of valence electrons. Okay, so hey, what I mean, you guys, is if you look at the periodic table, you've got carbon, nitrogen, oxygen, fluorine, right, and all the atoms beneath them, right? But hey, carbon's going to start out with 4 valence electrons, nitrogen 5, oxygen 6, fluorine 7, right, you guys? So what this means is that, hey, for example, say carbon, okay? So let's draw the Lewis structure for carbon. He's got 4 valence electrons that he starts out with directly around him, okay? And he always wants to maintain that number of valence electrons directly around him. He always wants to have 1, 2, 3, 4 valence electrons directly around him. And what does this mean, directly around him? Well, let's see in just a second, okay? Because, hey, this isn't to say that carbon doesn't want to fill its octet. It doesn't want to bond with other atoms, because it does, okay? So, hey, for example, if we had, let's just say, 4 hydrogens coming in to bond with this carbon, each with their own electron, right? Carbon still wants to bond with them, right? He wants to bond to each of these hydrogens so it can fill its octet and have 8 valence electrons total around him. But check it out, you guys, because carbon always wants to have 1, 2, 3, 4 valence electrons directly around him. Sure, there's these exterior electrons, right? These 4 exterior electrons that got added to it. But hey, carbon always wants to maintain those 4 valence electrons directly around it like this. Nitrogen wants to maintain 5. Oxygen wants to maintain 6. Fluorine 7, right, you guys? They want to maintain that number of electrons to be neutral. Okay, so what this means, you guys, is that, hey, if you take away one of those electrons that's directly around it, so say, for example, I take this away. I take the electron that used to be there away. Okay, so, hey, there used to be an electron that went there. If you take that electron away, remember, you guys, an electron, this is a negatively charged electron, right? Electrons stand for 1 negative charge. If you take away an electron that stands for 1 negative charge, that's like adding a positive charge. So you take away an electron that's a negative charge, that's like adding a positive charge. So guess what, you guys? If you take away that electron, you're going to put a plus charge next to that carbon. Okay, you took away 1 negative charge, that's like adding a positive charge. You put a plus 1 charge next to that carbon. That's the formal charge of a carbon that only has 3 valence electrons directly around it, okay? But hey, let's take the flip side of that and say that instead of taking away electrons, let's say that you give that carbon an extra valence electron directly around it. So now carbon has 1, 2, 3, 4, 5 valence electrons directly around it. And what does this mean? Well, carbon wanted 4 valence electrons directly around it to be neutral, right? You add an extra one, you add an extra negative charge to that carbon, guess what? You're going to be adding a negative charge to that carbon. So now the formal charge on this carbon will be a -1, okay, since there is one more electron than that carbon wants to have directly around it. Do you guys see that? All right, so let me erase this real quick and I'll give you another example. Okay, and let's just take the example that we took from our math way. Okay, so hey, we had an oxygen bonded to 1, 2, 3 hydrogens, right? And it had a lone pair up here. Okay, so hey, do me a favor and let's do this the conceptual way this time. Okay, so if you look at the periodic table, you guys, how many valence electrons does oxygen want to have directly around it? 6, right? Let's count how many it has around it right now. So, hey, oxygen is going to have 1, 2, 3, 4, 5. Uh-oh, you guys, you just took away one of the valence electrons that oxygen wanted to have directly around it. Oxygen wanted to have another electron right there directly around it. So, hey, you guys, if you took away one of those electrons, if you took away a unit of negative charge, that's just like adding a unit of positive charge. So, hey, you took away one of the electrons that oxygen wanted to have around it, that's like adding a positive charge. So you'd put a plus with a circle around it, right next to this oxygen, right? Because this oxygen wanted to have 6, now it only has 1, 2, 3, 4, 5. You took away one electron, one negative charge, that's like adding a positive charge, okay? And hey, if you go on to check the hydrogens in this example, you guys, remember hydrogen is all the way over here on the periodic table, and it has a valence electron, it has one valence electron, right? So, hey, how many valence electrons is directly around each of these hydrogens? Let me draw this in blue. There's one valence electron directly around each of these hydrogens, which is the number that it wants to be neutral, right? So, hey, you guys, up here is the number of valence electrons that these atoms want to have around them directly to be neutral, okay? Carbon wants 4, nitrogen wants 5, oxygen wants 6, fluorine wants 7, okay? All right, so let me give you one last example problem to make sure you have this down, okay? So, hey, let's do oxygen with just one hydrogen connected to it this time. So, let me give him 1, 2, 3 lone pairs, okay? So do me a favor and find the formal charge on this oxygen and this hydrogen. Okay, so hey, what you should be thinking is, okay, oxygen wants 6 valence electrons to be directly around it to be neutral, right? Let's find out how many it has around it right now. Okay, so hey, this oxygen has 1, 2, 3, 4, 5, 6, 7 valence electrons directly around it, right, you guys? So that means if you added an extra electron, an extra negative charge around that atom, that's going to give it a negative charge. So you'd put a negative with a circle around it next to that oxygen. Hey, for hydrogen, remember hydrogen wants 1 valence electron directly around it. And hey, does it have 1? Yes, it only has 1 valence electron directly around it. Okay, you guys? Remember, hey, hydrogen actually has 2 valence electrons total here because it's sharing one with oxygen, but it only has 1 valence electron directly connected to it. Do you guys see that? Okay, so in this case, hydrogen is going to be neutral. Okay, so make sure to go home and practice these examples in your textbook when you get home, okay? But all right, just to remind you guys of why we were even talking about formal charge in the first place, let's step back and look at the big picture, okay? So, hey, we were talking about reactivity and how to look for which atoms in a compound are going to react, are going to make bonds or break bonds, right? And I told you that there are 4 guidelines, 4 sources of reactivity that you should look for when trying to spot an atom that will react. Formal charge is the first and most obvious thing to check for when looking for reactivity. So my next question to you is, why is formal charge a source of reactivity? Why do we look for formal charge on an atom to see if it's going to react? Okay, so hey, let me erase this and we'll get that down.